Okay, hello everyone. I'm Michael, and I'll be teaching the first part of our Asymptotics exam review session. So the agenda for today is we're going to review big O, big omega, and big theta, and look at some visuals and get a good understanding of what those mean. And then we'll start moving into what worst case and best case is and how that corresponds with our big O, big omega, big theta. And then we'll start looking at some exam level problems and walking through those. So let's get started. So let's look at some symbols, starting with big theta. So big theta is going to be one of our useful tools for describing runtime. So the idea is we want to find some type of expression that will represent our runtime, and we'll be able to remove all of our lower order terms, coefficients, constants, because all we really care about is the highest order term. And so say we define some function t of n, which is going to represent the number of computer operations needed for our program. So this is the same as kind of representing a function that will represent the time our function takes for some input n. We'll say our program f of n takes t of n equal to 2n factorial plus 100 times 2 to the nth power plus n cubed plus 1 million times n operations to compute. Well, all we really care about is the highest order term for this time complexity function t of n. So we can just use the n factorial to describe our function or our program f of n. So in this case, we would say our runtime t of n is contained in big theta of n factorial. Essentially, our big theta is going to be used to show the order of growth or rate of growth. So here's a useful visual representing our big O or our big time complexity. So you'll see this is a graph of our functions, for example, that we might use to describe our runtimes. So starting at the lowest, we say we have constant, which is just described as theta of 1 for some constant. Next, we have logarithmic, which is just theta log of n. And we can disregard any type of base because the base of a log is really just multiplying some log by a constant. So we just refer to any logarithmic function as theta of log n or just log n. All right, next we have linear, which is just going to describe theta of n just by itself. You can see that as a linear graph right here. Next, we have linearithmic. You don't need to know this name, but this is going to describe n log n runtimes. And there are more functions contained between these, but these are the most popular, so that's why we're just going through these. You can think of functions that correspond to these types of runtimes. So quadratic would be an example of an n squared runtime. And you can see n squared is greater than n log n here. So we would say this function is contained in big theta of n squared. Moving on to cubic, that's n cubed, greater than n squared. Exponential is going to be some constant raised to the nth power. It doesn't necessarily have to be 2, but we just have 2 here for our example. And then the greatest one that we'll look at for now is factorial. And that's just going to be n factorial. So out of all of these, you can see that as we go to the left, we have our greatest functions. And as we go down and to the right, these are our smaller functions. And we only look at these for large enough n. As you see, if we look at really small n, they'll run in about the same time. But as we use exponentially larger n, we'll start to see the behavior of these graphs and be able to compare them. Okay, so here's a small example now for a big theta runtime. So given this function f, what do you think the big theta, in essence, the tightest bound we can place on our function f is? So you can think about it for yourselves or talk in the chat, and feel free to ask questions or anything if you have any. And we can assume these lines, some plus equals and some minus equals, are done in constant time for this problem. So they do theta of 1 work. Okay, I'm gonna move on. So the answer to this problem is number 4, big theta of n squared. So what is happening here is, first we look at the length of our array and we set that equal to n. And then we initialize some variable int sum equal to 0. And now we hit our first for loop. Well, this for loop is starting at value 0. We loop until I is going to be greater than or equal to n squared. And we increment I by 1 each time. And so I isn't manipulated in the body of the for loop. So we can say that this for loop is going to run n squared times, doing theta of 1 work each time. So this first for loop right here will be doing theta of n squared work. Okay, let's look at our second for loop. The second for loop is initialized to be j equal to n minus 1. And yes, there's a comment in the chat. This probably should be j minus minus, but it won't matter for this problem. I guess, yeah, this for loop would never, this for loop would never end if it wasn't j minus minus. But yeah, say this was j minus minus, then this would run n times because we start at n minus 1 and we go all the way to j equal to 0. And so this for loop does theta of n runs, and we do theta of 1 work for each time the for loop iterates. So we do theta of n work for the second for loop. So the program F is dominated by this first for loop right here, doing theta of n squared work. So we say our answer is theta of n squared. Technically, the exact would be theta of n squared plus n, but because n is a lower order term, we say that it doesn't matter because our highest order term is going to be our n squared, which will dominate the growth. So we only care about the theta of n squared. Okay, moving on to big O and big omega. Oh, sorry, there are some questions about this. So 1 would be wrong because it's not the tightest bound we can use. When talking about big theta, big O, or big omega, we need to get rid of all of the constants, coefficients, and lower order terms. So n squared is going to be our highest order term. And so we don't care about the plus n because our growth is going to be defined and characterized by this n squared term. So the correct answer here would only be theta of n squared. So yes, we had to go through this for loop a total amount of n squared times. And so this is what dominated our work. While we went through this for loop theta of n times, but the theta of n squared is our highest order term. So we say our function is theta of n squared. Okay, on to big O and big omega. So we see that big theta is used to represent our program for some like perfect function that we can describe its growth with. Well, this isn't always going to be the case. So we'll have some analogs for this for less than equal to and greater than or equal to. And this will be used with big O and big omega. So first we talked about big theta. This is going to be some analog for talking about the growth of f of n being exactly equal to some time complexity function t of n. Well, for big O, we say that the growth of f of n is less than or equal to some time complexity function t of n. And for big omega, we say the opposite. We say big omega implies that the growth of our function f of n is going to be greater than or equal to some time complexity function t of n. So given t of n, we can thus say that big O is an upper bound on f, and big omega would be a lower bound on f. So you can see this f of n being always less than or equal to t of n means that big O will always be greater than f of n, and big omega on the flip side would be always, or sorry, big O implies f of n is always less than or equal to t of n. Big omega, f of n, always greater than or equal to t of n, so that's a lower bound here. So how do we use this for big theta? Well, when big O and big omega are representing the same function, then that implies big theta exists, because if we're upper bounding and lower bounding on the same exact function, then these two functions must be equal, which implies our big theta is our function here. And so let's look at some visuals to understand this. So for big O, say we're trying to describe the time complexity of some function f of n. Well, big O here we would say is upper bounded by g of n for some constant c. So we could say that f of n is equal to big O of g of n, because as n goes infinitely large, g of n is always going to be greater than f of n. So this is the upper bound case. And the main idea behind this is when we're running our program f of n, this is really helpful to say that our program is never going to take longer than some function g of n. So we'll say that as time goes on, our worst case scenario for the program is running in g of n time. So on the flip side, for big omega, we can lower bound f by some g of n times a constant c. So here we're saying as n gets infinitely large, f of n is always going to be greater than or equal to some function g of n times some constant c. So as these two go infinitely to the right, c times g of n is always going to be less than f of n, which is our lower bound. So how does this play into our big theta? Well, when f of n is contained between two functions that only differ in constant values, so this function g of n is the same up above and below f of n, the only difference is the constant that we're multiplying it by. So you can see that if f of n is always less than or equal to c1 times g of n, and always greater than or equal to c2 g of n, in this case, f of n would equal big theta g of n. Okay, so how do we use these, and how do we use these with best and worst case scenarios? So our big O and big omega, like we just said, is going to be for our upper and lower bounds. However, they can be very loose and still technically be correct. So how do you see this? We'll say we have some time complexity function that represents our program, and it is equal to n log n. Technically, we could still say t of n is in big O of n factorial, and t of n is in big omega of 1. And that's because this function n log n is technically upper bounded by n factorial and lower bounded by our constant 1. However, this isn't the tightest bound. So when working with asymptotics, we want to look for the tightest bounds possible so that we can accurately describe our function to the best of our abilities. And so by using these kinds of upper bounds, big O of n factorial and lower bound big omega of constant 1, that doesn't really tell us the an accurate depiction of the runtime of our function. And so this is why we'll be searching for our tightest bounds when working with asymptotics. So when we're doing runtime analysis, it might not be possible to always represent our function in terms of just one time complexity function. In these cases, we will be using big O and big omega to represent our function f of n, because we can always upper bound and lower bound our programs, even when we can't find a big theta. And while it might seem that big O and big omega are kind of analogs for best case and worst case, this isn't always true. In fact, we will be showing that best case and worst case are going to be independent of our input n and actually depend on the characteristics of our functions. So let's look at a best case and worst case example. So here, looking at our program F, we want to find what the best and worst case runtime is. And it is possible to have multiple functions representing this best and worst case. So our best case could have some big theta that is different than our worst case big theta. But we could also have big O slash big omega representing either one of these. So I'll give you guys a couple minutes to work on this problem, understand it. All right, I'm gonna give people a little start to this problem if someone is stuck. So here we can see that our if statement is looking at the odd slash evenness of our input n, which is the length of our array. So if n is even, so if the length of our array is even, we will go into this if statement. And so if n is odd, then we will go into the else statement. So then looking in the if statement, we have another if statement. If random coin, which has a 50% chance of returning 0. So this is all random based. So if random coin is equal to 0, we do some program or function call that does theta of n work. Else, we do theta of n squared work. And in our else statement, we do theta of n to the 5 work. So it looks like our best case scenario is going inside the first if statement, because both of these do less than n5 into the 5 work, whereas our worst case would be going into this else statement. So I'll give everyone a little bit more time to work from there. Okay, let's see the answer. Okay, so for our best case scenario, like I said, the best case was we go into this first if statement, and then going on for best case, we want to do the least amount of work in the best case. So that would be this first if statement when we're running in theta of n time. So we can say the best case scenario is our input n is even, and our random coin flip gives us a 0. And so we go in and do theta of n work. So then we can say that in the best case, the runtime is theta of n. Well, the worst case we saw is going to be not going into this if statement. So n being odd and going into this else. And in this case, we do theta of n to the 5 work. So for worst case, we describe our program with theta of n to the 5, big theta n to the 5. So one thing to note here is our worst case and best case was not some aspect of the size of n, but more about some characteristic of n. So here we're looking at the best case was n being even, whereas the worst case resulted in n being odd. And so this is very common for our best case and worst case scenarios. So yeah, like it says right here, in this case, it depends on n being even or odd. But we could also have just equally have had something like random coin being in this if loop, and we would want to go into this if loop based on random coins output and not some characteristic of n. So it doesn't have to always depend on n. So if we wanted to talk about the overall runtime for this program, we would say that the program is lower bounded by big omega of n, because the least amount of work we can possibly do is this theta of n. So we have a lower bound of our program f by n, and the most amount of work we could do is this theta of n to the 5. And so we would say that we are upper bounded by n to the 5, which means we have big O of n to the 5. So you can see here that we use different notation to represent runtime and best/worst case. So best/worst case, we had theta of n and theta of n to the 5, whereas runtime, we had big omega of n and big O of n to the 5. So I think my fellow staff members are answering a lot of questions in the chat. If you have questions, feel free to type in the chat or raise your hand on Zoom. And actually, we'll have questions at the end of this too, if you have any questions you want to ask in person, but the chat is also open for questions right now. But I'm going to keep moving on. So I'm actually going to switch the presentation over to my boy Shrains now, and he will be walking you through some exam style questions and some tips and tricks. So give us a second to switch. I think you know already, but you're muted, Shrains, in case you didn't.
Also,
Just
you're not
realized.
screen sharing anymore, in case that wasn't intentional.
Wait, can everyone see my screen now?
Yes, you're good.
Okay, lovely. Awesome. So thanks, Michael, for taking us through a lot of the theoretical ideas around big O, big theta, and big omega. Everyone keep asking questions in the chat, and staff members will get to you. But essentially, yeah.
Would it be possible for you just to real quick go over again the difference between best case and big O and worst case and big omega? Because it looks like a lot of people are confused about that.
Right, of course.
Yeah.
Yeah, so I can give a quick overview. And again, if you have more questions, feel free to keep adding them in the chat. The idea is that with something like big omega and big O, you know that a function will never run faster than big omega. And you know it will, you know that a function will never run slower than big O, and it will never run faster than big omega. And that's basically what Michael was saying earlier, right? So if you can upper bound it by something, you know, and that's going to be your big O, you know, it's always going to be lower than that. If you can lower bound it by something, you know, it's always going to be higher than that. And that's the idea for big omega and big O. They're general bounds on the runtime of the function. Now, what the best case and worst case really are based on specific inputs. So over here, we can see that in a specific case where n mod 2 is going to equal to 0, then you know that you can run in theta n because you can go into this case, right? And I mean, this one gives the disclaimer, but the idea is, you know, this isn't the case where the input follows this certain if case. In the case that it's not going to follow that, then we know we're going to go into this other else case. So the idea, and I know there's confusion about when would you use big O and big omega for the best and worst case. And the general idea, and I think Anjali said this as well, is if we can only describe the runtime in terms of big omega and big O, then we're also going to have to use those for best and worst case. So if we can't get a theta, then sometimes we're going to have to use it. So here, you can say, let's say we didn't have these theta times, right? We can say that in the worst case, the runtime is theta n to the 5. And let's say this was not given as a theta, this was given as a big O. Well, then we'd also say the worst case is O of n to the 5. And we'd say the best case is going to be omega of n. Again, here the thetas are given. That's why we can give the worst and best case in terms of thetas. But generally, we can also do them in terms of O and omega. And these, again, these are not based on input. These are just the general runtimes, the worst and the upper bound and the lower bound, whereas best and worst are more specific.
So one way that was helpful when I was taking the class and someone explained it to me was that when you're thinking of using theta, omega, and big O, that's kind of on the axis of the size of the input, right? So you're bounding the function based on the as you increase the size of the input. When you think about best case, worst case, and general case, you're basically on a different axis altogether. You're on a different set of features. So basically, like for instance, in the example we have, right? Whether or not a number is even is independent of its size. A very large number can be even and a very small number can be even. So because of that, we can't just say that like there's a separate big best case and a separate worst case. And that's dependent on this feature that's independent of the size of the input. And same thing with random coin, because you're flipping a random coin, where that coin lands will be independent of the size of your input. So just the same way that we can get a big O, a big theta, or a big omega runtime for our function as a whole, we can have these same things appear when we're doing best case and worst case, depending on our function itself. So I think the best way to do these types of problems, if you are confused, is when you start doing best case, basically just ignore everything that wouldn't happen if you were in the best case. And just pretend like the function that you're running is like a subset of the function you'd be running otherwise. And then just run normal asymptotic analysis and then figure out whether or not your big O and your big omega meet at some point. And if they do, that's your big theta. If they don't, then you have a big O and a big omega, and those are your answers. I hope that clears things up. If you still have questions, you can post on Ed and stuff after this, okay?
Yeah, thanks a lot, Anjali. I think that really cleared it up, and I think that was much better than the way I was explaining it. But yeah, like Anjali said, like you can think of like even n being like a separate thing from odd n, and here you can have a big O, a big omega, and a big theta, and this is only for even n's, and the same thing for odd n. It's a separate thing where general omega, general O, and general theta are for any input that you may get, and it's as the input just grows. So yeah, I think Anjali explained it a lot better. So hopefully, again, if you do have questions, keep asking them in the chat, keep posting them on Ed, but just for the sake of time, we're gonna now move on to some exam style questions and some general tips and tricks. So I would very much advise you that if you're still not understanding like what theta is and what asymptotics are, like go back to the slides, go back to the part that Michael covered, and really make sure that you understand that, because otherwise these questions can be hard to approach. But once you feel a little bit more confident on that, the best way to get good with asymptotics is also to do questions, right? So hopefully you can pattern match, you can see little similarities, and that's what we're gonna do now. Is there any questions? Okay, awesome. So now I'm just gonna go through some general ideas that are really useful to keep in mind as you're going through these problems, and then we'll look at some examples of all of these works. So first of all, just some general ideas. Often with asymptotics, you're going to see nested for loops, especially in this class, because that is a case where asymptotics matter a lot, right? Because you're running through the elements twice, and obviously the worst case, the runtime can go really fast. So with nested for loops, anytime you see them, one thing to ask yourself is how are the incrementing and stopping conditions of the two for loops related to each other? So if the first for loop is based on I and the second for loop is based on J, are they in any way related? And if they're not, if the inner for loop is independent of the outer for loop, we can often just multiply the runtimes. Again, don't just take these as like formulas that you can apply, but just think about that. If they're not related, then it doesn't matter what the outer loop is. That just matters how many times the inner loop will be run, and then you can check how many times the inner loop will be run and multiply them together. If the inner loop is dependent on the outer loop, and this is also a case that we see a lot, it can be very useful to use a summation or just also write out the first few terms just so you get a general idea. Okay, yeah, sorry, I was checking the chat. Okay, generally in this class, the way we ask you to approach asymptotics is not to worry too much about the math behind it. That's more for classes like CS70, CS170. But two really useful things to know are that the sum of all natural numbers up to n is basically n times n plus 1 and 2, which just simplifies to theta of n squared, because again, we only care about this n squared term that's going to result, not the n on 2 term or anything like that. The other one is that the sum of the powers, the 1 plus 2 plus 4, 2, so the sum of the 2 to the I terms will eventually just come out to something like 2n minus 1, which is theta of n. Another thing that I would really keep in mind, and this is a really good thing to check every time you look at a problem, is there a return statement? Because if there's a return statement, often you might see a return statement in the inner for loop, and that means that if that return statement is ever met, the outer for loop might not run through all of its iterations, right? So just keep an eye out for when the return condition is going to be met, because that might affect your runtime. For example, if it always gets met in the first running of the for the full execution of the inner for loop, then the outer for loop won't even go to its second iteration. So things like that to keep in mind, and then think about, do I actually need to consider the full runtime of the outer for loop? For recursive cases, I know this is kind of obvious advice, but drawing a few layers of the recursive tree really does help to find patterns. And it's just so much easier than trying to work out all the math, which can get quite complicated. Once you draw out the few layers of the recursive tree, you can see how much it's growing at each layer, how they're dividing into different nodes, and we're going to go through some of those examples now. So you're going to notice that these questions are going to get harder, and we'll see a few of the cases we talked about here. So with this question, and again, we've taken previous midterm questions, so you can know these are the style of questions you're sort of expecting. So for this question, this one goes through two for loops, like we just talked about. And again, always the first thing you should notice is just pay attention to these over here, right? So where is it starting? What is it going till? And how is it incremented? So here we can see that it's going from 0 till n, and I is being incremented plus equals 1. And that immediately tells us that we're not worrying about anything log. It's just going to go from I equals 1 to 2 to 3 to 4, all the way till n. So this outer for loop is going to run in n time. Here we can see with this inner for loop, again, it's starting at 1, it's going till n. Differences like this don't really matter all that much. The reason we do have a 1 over here is because you're going to see we're multiplying the j by 2 each time. And that's because if it started at 0, well, it would never get incremented because anything times 0 is just 0. But again, you don't have to worry too much about thinking, oh, well, this one is going to go from 0 to n, this one's going to go from 1 to n. Again, that's just an off by 1. It doesn't matter too much. What really matters is where is it going till? So both of them are going till n. But whereas the outer for loop is being incremented by 1, the inner for loop is having this counter multiplied by 2. So let's break this down little by little, right? The first thing, going back to the tip that we mentioned, is are the inner and outer for loop related to each other? Again, just taking the time to clarify something like this can be really important to help you out. So here, anyone want to, well, it says they are independent, so I guess there's no point of asking, but yeah, they're independent of each other, right? In the sense that J's condition is not dependent on I in anywhere. We're not doing J less than I, we're not doing J equals J times I, anything like that. It is in some way independent. So now let's break this down little by little. First of all, generally for things like prints or ads, we just say theta of 1. It will usually be clarified in the question, but if it's not for something like print, you can just sort of assume that it's going to be theta of 1. Okay, so now that we know this runs in theta of 1 time, all we really care about is how long will this for loop run for, right? Because if what's happening inside of it is going to run in constant time, let's worry about how long this for loop is running. Anytime you see something being incremented by multiplication or you see it being decreased by division, your mind should automatically go to log. And the reason for that is that's exactly what a log is, right? It's taking some base to some power and giving you that value. And that's essentially what's happening here. J is going to go from 1 to 2 to 4 to 8 to 16, blah, 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 all the way to n. And that basically gives us log base 2 of n. We don't generally care too much about the bases. The logs are roughly equivalent to each other. So we're just going to say that's theta log of n, right? And that's exactly what we're seeing here. So this inner for loop is going to run in theta log of n time. Hopefully that's clear. And again, if there's any questions, feel free to ask. My fellow staff members will keep answering those questions. But now we've finished these two. And again, the reason we multiply is just because when I equals 0, this entire for loop is going to run, right? So it's going to do theta log of n work. Then when I equals 1, it's going to run all the way through again. When I equals 2, it's going to run all the way through again. And that's why we're multiplying. We're not adding the terms. It's because for each I, this whole thing is going to run. And that's why we want to find out how long I is going to take. I is a simpler case in this case. It's just doing plus equals 1. So if it's going to go from 1 to 3 to 3 and all the way up to n, I'm guessing you can guess it's going to be theta of n work. And that's why, since these are independent, we can just multiply these two together and get theta n log n. So are there any questions about that? Yeah, so the inner for loop is not constant time. The print statement is. Sorry if that was a little bit confusing. And generally, again, for prints and things like that, we just say they're constant time. So hopefully this is something that you guys have seen a lot by now, but this is a good starting point, right? So we've established some principles of checking how the for loops are related to each other. So let's go to a slightly more complicated question. What would happen if the print statement was replaced by an operation that is not constant? We'll see some examples of that. And there are cases that we do think about that, right? There are cases where we think about when it's a recursive call. But generally, let's say we said this inner thing over here, this print statement was ran in theta of n. Well, then there's going to be log n of these n's. So that's going to give n log n, and then that's going to be multiplied by n again. So that would be n squared log n. But again, we'll see some examples of that if that's not exactly clear. But generally, with the work actually taking some time, it's usually a recursive call or something like that. And it will be given to you. Like we'll tell you how long a print statement runs it. Okay, so this is a spring 2015, and it's from the final. So hopefully, if you guys were planning to do the 2015 midterm, I'm not stealing questions for you. Okay, this one's a little bit trickier, right? So let's go through that same process again. And again, the first few things that we, did the pointer just go away? Oh, it's back, sorry. The first few things that we should notice again is that what is the starting condition? What is the ending condition? So here you see a difference. Yes, this starts at 1, this goes to n, but now it's the outer for loop that's being multiplied by 2 each time, and the inner for loop is being incremented each time. But now we can see that they are actually dependent, right? J is less than I. Therefore, you can't just multiply these runtime because this one is going to be a varying runtime. So the first time it's going to take a different amount of time to the second time when I equals 2 instead. But yeah, so again, we assume that something like a sum is just plus equals 1. It's O of 1 or theta of 1, however the question decides to give it. There is no return statement. So again, that's just something to keep in mind. We are going to always run through this whole thing, right? So we're not going to just stop halfway. And yeah, J in the inner for loop increments by 1. I in the outer for loop is multiplied by 2. So any question? How do we find it? It was log n for the previous example. Hopefully someone on Coursera can get to that. If there's still questions on the log n question, I'll get back to that later. Okay, so let's start with the outer for loop over here, right? So we're saying I equals 1 and I have to get till n and we're multiplying by 2. So that means I is going to follow this pattern of 1, 2, 4, all the way till n. And generally, once again, every time something is being multiplied, we can just say this is equivalent to log n iterations, right? Because log base 2 of n will give some value, which is basically how many times you have to how many times you have to raise 2 to get to n. That's the idea. So we have to raise I 2 log n iterations to get to n, right? That's the general thought process. Again, don't worry too much about the math of it, but generally the idea is every time you see a multiplication, just think log. If it was being multiplied by 3 every time, it would be log 3 of n, but it's still log of n for our purpose. Okay, so that's the first thing we notice. And again, for the outer for loop, it's not really dependent on anything else, so we're set with that. Now, one very common trick that everyone uses is that once we've established the outer for loop is going to be log of n time, we're going to now think about the inner for loop. And like I said, it can be really useful to just write a few examples out, right? So we can say when I equals 1, how many times will the inner loop run? When I equals 2, inner loop runs. I equals 3, inner loop runs x times. Can anyone tell me an error with doing this? Is there any mistake I'm making going from this to this? And I'll just look at the chat. Exactly. I think you guys figured it out right away. It's never going to equal to 3. So just be really careful about this. And this is sometimes like a quick mistake. It's like the stress of the exam. You're working fast, so a little mistake like this can happen. But keep in mind how the actual outer loop is being incremented. It's never going to hit 3. It's being doubled each time. So don't do this pattern because it'll give you the wrong pattern. So yeah, remember how I update? It's multiplied by 2, it doesn't get incremented by 1. So now we can still use the same process, but let's actually do it right this time, right? So when I does equal 1, well, how many times will j run? So right now, ignore this outer for loop and just assume that I has a fixed value here. If this will let me annotate. Assume that I has a fixed value here of just 1, right? Well, j is going to equal 0, j less than 1. So it's going to add 1 and j plus equals 1. So it'll just run for 1 iteration, right? Pretty straightforward. What's the next value of I going to be? It's going to be 2. So again, the same time, it's going to go through, add 1 to the sum, go through again, add 1 to the sum, and then j will equal 2, so it'll stop. When j, and hopefully you can see the pattern that's kind of building here. It's basically whatever the value of I, that's how many times j is going to run, right? Because again, we're plus equaling 1, so we're not multiplying by anything, so it's going to run I times. And now, once we have this idea that the outer loop is going to run in log n time, well, it's going to have log n iteration, and the inner for loop is just going to be up to the value of I. Let's actually look at 2 ways we can now approach this. Okay. So the first way is just, again, like we just talked about, it's going to go through 1, 2, 4, 8, so on and so forth. And there's going to be log n of these terms. So this is a little bit tricky, but substitute I equals. Okay, so I see that people are already making some attempt. I'm glad you guys are thinking about it. And again, don't jump ahead of yourself. Let's just take it step by step, right? So exactly like you did say, it's gonna, at each time, it's gonna take I time. And it's going to go 1, 2, 4, and there's going to be log n of these terms. And hopefully you can realize they're going to be log n of these terms because there's log n iterations of the outer for loop, right? So now let's look at 2 ways to basically put it together. What you can realize is that, well, the outer for loop really just controls how many times the inner for loop is going to run. So instead of just multiplying these 2 values together, we can just think of it as adding up the number of times the inner loop runs, right? Because again, that's really the purpose of the outer loop, is to check how many times is to control how many times the inner loop will run in this case, because it's dependent. So the first time when I equals 1, it's going to equal 1. The inner for loop will run 1 time. The second time when I equals 2, the inner loop will run 2 times. The third time when I equals 4, the inner loop will run 4 times. And again, this should look like something you guys have seen before. It's the sum of the powers of 2, and that just comes down to theta of n, right? So even though we were dealing with a log n term over here, essentially that log n term just controlled how many different values there are. And once we sum up over all of those, we get theta of n. I see there's a question. Yeah, do you want to unmute him?
Yeah, so I thought since the outer for loop is going log n times, the inner for loop is only going to be able to go max log n times, right? So shouldn't it be log n times log n?
That's an interesting question. So let's think about that, right? So first of all, the inner loop will actually go up to, the outer loop will go up to n, right? It's running for log n iterations, but the I is actually going up till n. that means at some point the inner loop will also have n iterations,
Oh,
right? So
okay,
that,
I see that. That makes
yeah,
sense.
exactly. It's a little bit tricky, but just notice the stopping condition here. This is going to have log n iterations. So again, that's a really important thing to distinguish between how many iterations there are, but how many iterations of the inner loop. So hopefully that makes a bit more sense. Does that kind of answer your question?
Yeah, thank you.
Okay, awesome. So yeah, hopefully that makes a little bit more sense. And again, this is a tricky question, so don't worry about it too much. But the general idea is the outer loop is just controlling how many times the inner loop will run. They're dependent on each other. Well, the inner loop is dependent on the outer loop. And that's why it comes down to this familiar thing. Approach number two, if you are the type of person who does prefer the mathematical approach, you can also think of it like this. Basically, on a given value of I, the inner loop is going to run 2 to the I times, right? So when I equals, I know technically it starts at I equals 1, but just because j is starting at 0, it basically converges to this sum because of the minor difference there. But generally, this is the pattern it's going to take. And then because we are dealing with asymptotics, we just worry about the biggest term. This is not actually an equals, it's like roughly equals, and that's going to be 2 to the log n. Since it's a log base of 2, it cancels out. And that's basically going to be theta of n. So again, it depends however you approach it. I wouldn't worry too much about the second approach. If that makes no sense to you, that's totally okay. Do you not multiply because the two loops are not independent? Exactly. Because the two loops are not independent, you can't just multiply, because if you multiply, you're assuming that for each iteration of the outer loop, the inner loop runs the same number of times, but it doesn't, right? So for each iteration of the outer loop, the inner loop actually depends on the value of I, so you can't just assume it's going to be a constant. Again, this is a tricky question. Hopefully I can look at a few of the questions. How do we know just to add up 1 plus 2 plus 4 plus 8? Okay, that's a good question. Essentially, by adding up 1 plus 2 plus 4 plus 8, what we're doing is just counting all the iterations. So this approach here is literally just counting the number of iterations that we go through, right? So when I equaled 1, we got 1 iteration of the inner loop. When I equals 2, we got 2 iterations of the inner loop. When I equals 4, we got 4 iterations. So essentially, if you add up all of these, you basically get how many iterations there are of the inner loop, all summed over all the values of I. And that's why we're adding them up. That basically gives you how much work we did, and that is theta of n. There's log n term, but the thing actually adds up to theta of n. So we don't multiply.
To jump in very briefly, just because some people
Yeah.
seem to be confused about where the log n plays into this. So where the log n plays in is, if you notice, it's actually the number of terms in our summation. So it looks like it completely disappears, but it doesn't quite disappear. So you go from 1 to 2 to 4 to 8, and doing that causes us to go, that's like a log n increase, or not log n, but that means there's log n terms in our thing, right? So if you think about it, if we didn't multiply by 2, if we added 1 to I at every iteration, we would have a different runtime. We would have n squared instead, right? You've seen that one before in, I believe, discussion. And so that's why you do have to still pay attention to the order of growth of the outer function, even if it may or may not appear physically in the final result. It's still there underlyingly.
Exactly. Thanks, Anjali, for clarifying that up. Hopefully that does clear things up a little bit. But yeah, so there's log n terms here, and that's how we get to this idea over here. And again, there are log n like individual values here, and that all just adds up to theta of n. I'm going to look at how did you come up with a 2 to the I equation? Again, I won't spend too long because you're not required to know the math, but the general idea is that the number of iterations that the inner loop runs for is being doubled each time, because again, it's dependent on I, and I is getting doubled each time. So that's how we get the 2 to the I, because every time I increases by 1, this value is going to get doubled, and that gives us these iterations. If you're too confused about that, again, don't worry. I just have that in there in case some people do prefer looking at the math version. Okay, I think Arshi is answering a few of the questions. Yeah, okay, so hopefully Arshi is answering a few of the questions. Again, I know that's confusing, guys, but I would come back and revisit and just keep the principles here. It really does help to look at the difference between the previous case where they weren't dependent, where they were independent, where we could just multiply, whereas this case, they are dependent on each other, which is why we can't multiply and we add up instead, or we take this summation. Okay, For the sake of time, okay. For the sake of time, I'm going to move on to the next question. And this is going, again, putting it all together, we get theta. Okay, this question is, again, it's a little bit of a tricky one. And the reason I want to go through is hopefully we can work through it together and it'll be a little bit clear to everyone how exactly we got there. So this one's tricky in the sense that we're actually giving you two inputs. We're giving N and M. And again, this is from the spring 2015 midterm. And we're asking you how the asymptotic growth is. And so it might fully be dependent on N. It might fully be dependent on M. We don't know yet, but we're going to actually try to find out, right? So again, whenever you start a question, don't just start like trying to jump in and write the math out yet. Just notice a few simple things. First of all, you can see that this for loop over here. So in the beginning, let's just ignore this, right? Like we don't really know what this is yet. So for now, let's just ignore this. Let's go to the else case because we usually assume that, well, M is going to be given as some value. We're not just going to get the easy case where it's 0. So let's say that M comes in as a value. Notice that this for loop is entirely based on N, right? There's no sense of M here. And this for loop is just going to run in, it's going to have, oh, I'm not going to write the data yet. It's going to have N iterations, right? Sorry, I'm not very good at writing with my mouse, but this is going to have N iterations. There's no sense of M anywhere. But what happens in each of those N iterations? Well, we do a recursive call, right? In this recursive call, again, the few things we should note for is how are the parameters being updated? We see that N is not being updated, right? So N really doesn't, like it's always going to stay as N. So we know eventually when we draw the recursive tree, N will never change all the way down because we never do change it. But M is being changed, right? M is being decremented by 1. It's not divided or anything. It's just a simple decrement. And what do we realize? Now we can go back to this case and see, okay, this is basically the base case, right? This is going to be the base case over here because whenever I hit M equals 0, when eventually the recursive tree gets there, I'm going to stop. And that's where the return is. So I can't really, there's no early termination. It's going to return when M gets to 0. So putting those notes together, and I think I should have them written out. Yeah. We can see the base case is based on M. So the recursion in a sense is very much based on M, but the iteration is based on N. Within the for loop, I is being incremented by 1. Again, always pay attention to the incrementation. It's going up till N. And within the recursive call, M is being decremented by 1. So hopefully that's clear so far. Any questions about that? Yeah, okay. I think she's answering questions. Awesome. So then I'm going to move on. Okay, so like I said, the recursive tree really helps here, right? So once we start with the input case that we have, which is just N and M, what do we realize? Well, we can see that for every single iteration in this for loop, we're creating a new recursive call, right? And so, and each one just has the same value of N, like I said, but the M is decremented. So these are going to be my children in this recursive tree. And anyone want to tell me how many of these calls I'm going to get? So I can take a look at chat. Okay, awesome. I'm seeing some N's. Awesome. Yes, I'm glad everyone seeing that again, right? It's just, even though this looks confusing at first, we can break it down step by step and we realize, well, there's just going to be N of these calls. Okay, cool. So that's where we're at right now. Now let's go to one more, let's go down one more layer, right? And again, maybe on an exam, you won't have that much time. You don't have to write it this formally, but the principle should stay. So with the recursive tree, what really helps is once we've drawn this first layer, and hopefully everyone can see how I've gotten everything in this, like this region. That is a wonky box, but now let's just focus on one of these nodes, right? Don't think about the whole thing yet. Let's just focus on one of these nodes. Let's say that I call my function f with n and m minus 1, right? So I'm going to go in. I'll say if m less than or equal to 0, let's not hit that base case yet because I'm assuming we haven't. I want to keep seeing how the recursive tree will develop. So what am I going to do now? I'm going to run a for loop. I'm going to run a for loop that runs the number of iterations as the first parameter. what's nice is n hasn't changed. So I know I'm still going to have n iterations, and I'm right now at n-1. Using the same pattern we saw before, what we can now say is that this node is now going to have n children of its own, right? It's going to have n recursive calls that are labeled here. And each one of them, well, this started as m-1. So when we're at m-1, we decrement it even further to get m-2s over here. Hopefully everyone can read that. I know that's kind of small. Okay, so now we can see how this recursive tree is developing. So each time a node will have n children, and each of its children will have its value of m-1. And so we can see that if this node has n children, then this node is also going to have n children, and this node is also going to have n children, and this node is also going to have n children, and this node is also going to have n children, right? So that's the first thing that we can notice. Let me see in the chat. The for loop runs n times. How do we know? Okay, yeah. So hopefully that's getting cleared up. Awesome. So yeah, the reason it's m-2 is because we decrement this each time. And I know here it says m-1, but you have to remember this m is going to be passed in as this new value. So when it gets decremented even more, that's why it becomes m-2. Okay, now let's think about what we said earlier, right? When we're drawing the recursive tree, we want to know the height of this tree. We want to know how many layers it's going to have. And we said the base case is completely dependent on m, right? N has nothing to do with the base case. It's dependent on m. And we're basically going to stop when m equals 0. I know it says less than or equal to, but since we're starting at some positive value, presumably we're going to say that it's going to stop when m equals to 0. So if each layer is decreasing m by 1, how many layers am I going to have? M layers. Awesome. Yeah. Okay. So hopefully that's clear. It seems like a lot of people are getting that. If you're not sure how we got that, feel free to ask a question about that, but we're going to have m layers, right? And so now we know that each time you have a node, it has n children, and there are going to be m layers. So let's start putting it together, right? And again, I'm going to give you 2 ways to do this. If the math way doesn't make any sense to you, please do not worry. We're not expecting it to, but some people do prefer that way. So I'm actually going to start with approach number 2. Intuitively, we can say that the last layer is going to have the most nodes, right? Because obviously you can see this tree is going to get really, 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 really big, right? So the last layer is going to have the same number of nodes, the most number of nodes. Now in layer 0 here, we saw that there's essentially 1 node over here, right? Then in layer 1, we said that there's n nodes over here because we said this node is going to have n children. Well, each of these also had n of their own children. So if there were n nodes here and each of them had n of their own children, we get n times n equals n squared nodes on this layer, right? On this case over here, we can see that, well, each of these n squared children is going to have n more recursive calls. So we get n squared times n, and that's going to give us n cubed. Hopefully everyone can see how I'm getting that. Okay. Yeah, hopefully everyone can see how I'm getting that. So if we know that each time we're increasing the number of nodes by a power of n, we're basically multiplying it by n, how many nodes are there going to be on the last layer? Anyone want to tell me? You can take a guess. You can take a minute to work it out. We can just take a minute and then feel free to discuss it as well. N to the m, n to the m. Okay, seems like everyone got there pretty fast. Awesome. So there is going to be n to the m, right? Again, if you are the type of person that likes the math, with recursive trees, you can generally think of it like this, right? I'm going to sum from I equals 0 generally. Yes, I see there's a question. Do you want to unmute yourself and ask a question?
Yeah. So are we only looking at the bottom layer when we look at these recursive elements, or are we supposed to add everything up?
That's a great question. I'm really glad you asked that, right? So let's think back to what Michael said earlier. Remember when we said we have something like n squared plus n? We don't really care about this because it's so much smaller in the limit. So this just becomes theta of n squared, right? In a similar fashion, what we can say is that based on what everyone said in the chat, and you guys are right, the last layer will have n to the m nodes, right? But the second last layer will have n to the m minus 1 because it's 1 up. So it's going to have slightly less, and so on and so forth. And again, asymptotically, with something like this, we only really care about these. Because I know it may not seem like a big difference. You're like, oh, when like n and m are really big, these two numbers are going to be really big. But when we're thinking about like the billion, there's actually going to be a significant difference. And all that really matters asymptotically is this biggest case. So we just kind of discard all these extra terms over here, and we just think about the last layer. Does that make more sense?
Yeah, it does. Thank you.
Okay, awesome. Glad that worked out. Okay, cool. So let's just look at the math version for the people who do prefer the math. If we do layers and we do work per layer, also, yeah. And if you think about it, the work per layer is essentially, again, please don't worry about this if you don't like the math stuff, but the work per layer is essentially just running the for loop, right? So on this layer, it's going to take n times, and I think I should have started my i's at 1. Sorry, I think that's a slight off by 1 error. Yeah, so essentially at this layer, I'm going to run the for loop n times. So that's n work. On this layer, each of these is going to run the for loop n times, and there's n of them. So that's n squared work, and so on and so forth. So it basically becomes this summation. And again, in the asymptotic case, we don't really care about the lower terms. So this roughly equals n to the m. This is the math version. You don't have to worry about it too much. And hopefully everyone can see that y approach 2, just counting them will give you. I see there's some questions about why is it not log m. The reason it's not log m is because we're decrementing m by 1 each time. So we're doing m minus 1. If we were doing m divided by 2, then it would be log m, right? Because there's like a multiplicative factor of half. But since we're decrementing by 1, we'll get m layers. And putting this all together, we see that, I'm just going to clear everything up. O and n, theta of n to the m. And hopefully everyone can see how we got there. So again, a difficult question for sure, because there's 2 variables, there's recursion, there's iteration. But hopefully you can see just asking yourself some basic questions about how many recursive calls is each node going to make, how are they going to grow, what variables is the recursion dependent on, what variables is the iteration dependent on. Just ask yourself these questions one by one, and it'll build to give you the answer. And hopefully that makes sense. Yeah, Preeti.
Yeah, so is this related to the whole branching factor term where it's like the number of branches raised to the height of the tree? Is that something we can use?
The number of branches raised to the height of the tree. One of the other, I believe one of the other people on course staff, I don't explicitly remember seeing that formula. Anjali, do you want to?
Sorry, can you repeat the question?
Yeah, so I heard from previous problems where if we have something that's recursive, we can use like the branching factor to the power of like the height of the tree. Is that like the standard formula we use?
Okay, so the thing I always say every time I teach asymptotics is there is no formula, there is no general method for any asymptotics problem because every function is different, everything branches differently, everything has different ways of running within each node and stuff, right? So that's a good starting point perhaps. So that might be a place where you can start. But in general, especially with 61B problems, because we try to give you guys problems where you can physically like draw things out to a certain extent and kind of use your intuition from there. It's usually better to draw out some parts of the graphs, try to build an intuition around like what dominates and stuff like that, because I hesitate to ever say that a formula will always work because a formula is never going to always work when it comes to asymptotics. In 170, you'll learn a couple formulas that work in very certain situations, but even they don't work in every situation, which is why we don't teach you them in this class. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah. So yeah, my recommendation always, I'm a graphical person though, is to draw things out. If you're like more of an equations person, I'd write out like terms and figure out how to sum them or multiply them or whatever. But I hesitate to say use a equation, because when you use an equation, you kind of abstract away a lot of what's happening underlyingly. So you might miss stuff that you wouldn't otherwise miss.
Right. Thank you.
Yeah, and just on that point, even things like this formula I gave you, like again, it's not, first of all, it's not really that much of a formula, but it is based on this case, right? It's because there's just the work per layer, I had to still work it out. So again, it's not gonna always be n to the I, it would depend. So if you are the mathematical person who does like taking a summation, make sure that you're not just summing in some general term in here. It has to be related to the tree. Yeah, Adam, I see you have a question.
Hey, can you hear me?
Yeah.
Hi. So I got to the point where I got the sum of like n plus n squared plus n cubed all the way to n to the m, but I didn't realize that like it was the last term was big enough so that all the other terms beforehand don't really affect it. Like how come in this case I knew that it would just be n to the m versus like when we sum up all the natural numbers, we don't just say, oh, because n's the last term and it's the biggest term, it's theta n. When we sum all the natural numbers, it's theta n squared.
Right. So first of all, thank you so much for that question. And let's just, speaking of which, let's just go back to this term, right? I think generally first of all, what you're seeing here is that there is, with this equation, there's an incremental increase. It's like plus one, plus one, plus one. Whereas in our case, it's an increase by an order, right? So in our case, when we were doing the tree, like there was an increase by an order of n each time, which is why we can say the lower terms kind of fall away. Here, it's like adding up. So for example, let's say I did 1 plus 2 plus 3 plus all the way till plus n to the m. That would not be n to the m, right? Because you've added up all of these lower terms, and that will actually like give you something like n to the 2m or something like that. But because we'd be adding up every single lower term than that, in this case, we're multiplying by a factor. So it's entire order of growth bigger than the previous layer, which is why the terms sort of fall away. I hope that makes a little bit more sense. Again, generally, what I would just try to remember is that if there is a difference by like a power, you can usually ignore the earlier terms.
Okay, yeah, that makes a lot of sense. Thank you.
Okay, awesome. Glad that helped. Let me see if there's any more questions in the chat. Okay, looks like you guys are answering each other's questions, which is also awesome to see. But yeah, so hopefully you can see we've gone through 3 examples now, one with independent for loops, one with dependent for loops, and one with recursion plus iteration. This is a tricky question, so if you guys are getting this, that's great. But for the last question, some quick key takeaways. Yeah, so important to know which variables are related to the recursive case, the iteration. Here, even though it might have looked like 2, you can see they were sort of like, they had different purposes. N was for the iteration, M was for the recursion, so that helped. Drawing the recursive tree does help. It doesn't have to be like this nice and neat, but just drawing like even 2 layers, you can kind of see the pattern. And yeah, the formulaic breakdown and the intuitive analysis are both valid approaches. For the formulaic breakdown, what I mean is like doing the math and trying to take the sum. Don't just like, again, like Anjali said, don't just plug into some formula. You might be updating values wrong or something like that. But yeah, if the math doesn't make sense to you, just counting and seeing how things are going is also a very valid approach. So with that, I'm actually going to pass back to Michael for the last question of the day, and then we can just take some questions from the audience in general.
All right, hello everyone again. I'm gonna be walking us through the last problem for this session. So this is the problem. F4, we want to find our tightest bound on our function F4. So I'll give everyone a couple minutes to start, then we'll walk through it. And feel free to bring up any questions you have in the chat, and we should be answering them. All right, can people say if they need more time or if they're done or not, so I can know whether I should start? All right, a couple more minutes, no problem. Okay, I'm gonna start describing some things just in case some people are stuck, but we won't get the answer just yet. So for recursive problems, there are some things that we want to look for, like some important attributes of recursive runtime problems. So one of them being the branching factor. Like we saw in the last problem, we were branching by a factor of whatever our m variable was. Whereas for this problem, we have 4 recursive calls to F4. So for each node, for each call to F4, we're going to have 4 new nodes branched off. We're going to have 4 new function calls. Okay. And then another thing we want to know is how is our input decreasing over time, or if it even is decreasing. So our input here is halving at each level. And this is going to be important to find out the height of our runtime tree, of our recursive tree. Okay, another thing that's important to know is how much work is being done per node. So these recursive calls aren't doing work necessarily themselves inside their own respective nodes, they'll be doing work. But we see after we're done with our recursive calls, we have this function call to g of n, and that is going to be running in theta of n squared time. So at each node, depending on what our input n is, for example, for each recursive call, n is halved by 2, we're going to be doing theta of n squared work. So putting all of these things together should allow us to start finding our total runtime. I'll give everyone a couple more minutes or a little bit more time to start working this out. Okay, how's everyone doing on time? Feel free to message me message in the chat if you need more or if you're ready. Okay, it looks like people are starting to be ready. So we'll start. Yeah, we'll take a look at how G of n is going to be affecting our total runtime. Okay, so in response to the latest question, we're not necessarily going to be doing any type of multiplication here, at least not yet, because this is a recursive tree, so it's a little hard to just be multiplying F4's runtime with some kind of G's runtime. Instead, we want to be looking at like the layers and the total number of nodes we have. So let's look at a recursive tree. So starting with F4, we take in some input in, and we do 4 recursive calls of size n over 2. So our branching factor is going to result in 4 new nodes being created. Hold on, I'll make a pointer. So yeah, we have these 4 new nodes that are being recursively called, each with an input size of n over 2. And so after we do these 4 recursive calls, I mean, each of these will have their own recursive calls, but the total amount of work being done for each node is equal to n squared of its size. So we can see the original node will be doing n squared work. And then each of these nodes are going to be doing n over 2 squared work. So for example, this singular node will be doing what, n squared over 4 work. This node, n squared over 4 work. This node, n squared over 4 work, and same with the last node. And so these pinkish red boxes are representing the amount of work associated with each node in the tree. So the approach here now should be, can we find out how much work is being done per layer, and then just sum up the number of layers that we have. So because 2 might not be enough to see a pattern, let's take it 1 level deeper. So let's see, this recursive call has 4 of its own recursive calls of size n over 4. So n over 4 squared is going to be n squared over 16. And the work done, or the number of nodes in this next layer down here, will be 16 nodes, because each of these nodes have a branching factor of 4. So we can see that we'll have 16 nodes in the next layer, all doing n squared over 16 work. Our second layer right here was doing n squared over 4 work for each node, and our top node is just doing n squared work.
Sorry to jump in real quick, but I think there's someone who has a hand up, so I figured if you wanted to answer that.
Yeah, I didn't see that. Yeah, feel free to unmute, and ask a question.
All right. The only thing I'm a little confused about, that I usually confused about with recursion. So can you break it down a little bit more, like line by line? So after f of 4 calls the n, after you call the n over 2, how does that branch out? Like, does it go, like, how does it keep on iterating through? Like, let's say the number was 4, it passes 2 back in, and then it passes 1 back in. Then does it go to the next one, and then do it again with 4 again, and then do 2 again?
Great call. Great question. Yeah, so right here, how I'm describing it, I'm not looking at the exact order of operations that's happening. In the actual program, we would do the first recursive call, and we'd go down, say this was the node representing that first recursive call, and then we do another recursive call, all the way until we hit the bottom. And when we hit the bottom, we have this n equal to 0. So that's when our input n was equal to 0. And once that happens, we go back into our program. So then the second bottommost layer would then get this call done, and it would go down 1. It would finish because we're at the second most layer. Okay, and then we would go back and we would finish this call, and then we would go back and we'd finish this call, and then we do the G of n work. So the order is actually a little bit confusing because we go all the way to the bottom and we do our work, and then we start working our way back up, and then we'll go down to the next one, all the way to the bottom, and repeat that work. But what this recursive tree here is doing is it's mapping out all of those nodes at the same time. So we know that the top node is going to result in 4 new nodes. It might not result in those 4 new nodes right away, but overall those 4 new nodes will happen. And so after the first node is created, it'll keep going down, but we can view the recursive runtime tree like overall right away by just taking in what the branching factor might be, which is equal to like the number of recursive calls happening. And so here we have these 4 recursive calls, which means that we'll have 4 new layers for each node in our recursive tree. And so after all of these layers are created, we'll be doing these g of n work for each node. So after like this subtree of n over 2 has created all of its nodes, this work is calculated to be n over 2 squared. But we don't really care about the order of the work we're doing. We just care about the total amount of work we're doing. So yeah, this n squared work here doesn't happen until everything below it has been created and all of their work has been calculated. But that doesn't necessarily matter to us because again, we're only concerned with the total amount of work. Does that answer your question?
Kinda. Just like as like an example.
Yeah.
So if we do like if we pass in a number 2,
Yeah.
for the first f of 4, would it just do? Would it go down the line and go n over 2, which is 1, and then go down, and then it would pass in the next one.
Yeah.
So
So it would create 4. Yeah, I'll just walk through a little example with n over 2 or equal to 2. So say this was 2. So it would then create this node with value 1, and then it would create 4 nodes down here of value 1 or value 0. So we'd have 4 new nodes down here with value 0. Okay, then this n over 2 is done. So we go back here, and then we call the next f of 4 of n over 2, which is 1. And we repeat the same process for here. So we had 4 new nodes of 0. And then once those 4 new nodes are created, we do the g of n work here. And then we'll go back up to the top one and we'll do the next f of 4 n over 2. So then this is created. And then we create the 4 new nodes down here. We go back here, we do the g of n work. And then we go back up and we do the last recursive call f of 4. Step into this node, create this node. We create the 4 subnodes underneath it. Come back to here, do our g of n work. And then last but not least, we go back to the top and we've done our 4 recursive calls and we can now run g of n on the original node, which will result in our 2 squared work. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, no problem. So yeah, that's a nice small example to kind of understand how this tree is being created in the first place. But now that we have an idea of how this tree was created, oh yeah, Hillary, do you have a question?
Yeah, so how do we know how many times we're running n divided by 2? I know there's ellipses where it continues and it's not just running for 4 times. How many times would it be running for?
Yeah, that's a very good question. So we are calling this recursive call 4 times for any given node. But I think what you're concerned about is how far down do we go? And so that's going
Yeah.
to be dealing with the height of the tree. And so we can find out the height of the tree by understanding how n is decreasing. So at each level, n is being divided by 2 until it hits 0. And so like we saw with previous examples, this is characteristic of a logarithmic function. So it'll take log base 2 of n calls to make n equal to 0 if we divide it by 2 every time. So you can see that in like a number of ways where if we worked our way back up, we would have 1 plus 2 plus 4 plus 8 plus ... to n. And the length of that sum would be log base 2 of n. And I think we saw that on previous problems, so it might be a bit familiar. But yeah, the height of this recursive tree is going to be characteristic of how we divide and how we're decreasing n for each call. And so here are the height of the recursive tree will be n log base 2 or log base 2 of n. Does that make sense?
Yeah, so I'm sorry, I wanted to clarify, what about for each layer? Like how many calls are we gonna make for n divided by 2?
Yeah.
Because I thought it would be 4, but then each layer, it's more than 4.
Yeah, so that's dependent on like the number of nodes we have in each layer. So for the topmost layer, we had 1 node. So the layer behind or the layer under it will have 4 times as many nodes because we have a branching factor of 4. So 1 goes to 4. The next layer, each one of these nodes will create 4. So it'll be 4 times as big. So the next layer will have 16. Then the next layer 64 and so on. So we'll be multiplying by 4 for each layer. So the
Wow.
bottommost layer will have what? I know there's some mathematical term for it, but I can't think of it off the top of my head.
I think it's 4 to the log n, I believe.
Okay, yeah, 4 to the
Also,
log n.
yeah, Hillary, sorry. The ellipses are kind of unnecessary here. The second layer has exactly 4 terms in this
Oh,
specific
okay.
case. I know, I was also confused looking at it for a second.
Oh yeah, I'm not sure why these are here. Yeah, don't mind
Okay,
the
thank you
ellipses
so
are here.
much.
Okay, so now that we understand the height of the tree and the number of nodes per layer, let's try to understand how much work is being done per layer. So at the topmost layer, we do n squared work. The next layer, let's try adding up all of the work done per node. And this work is coming from this g of n term, where we are doing theta of n squared work for each node. So here we have n squared over 4, and this will be the same for every node here. And because we have 4 nodes in this layer, we can say 4 times n squared over 4 will equal n squared work for this layer. So we have n squared work for this layer, n squared work for this layer. So we might be seeing a pattern here, but let's go to the next layer. So say we have our next layer with 16 nodes with input n over 4. Well, the total amount of work done for a single node is going to be equal to theta of n over 4 squared, which is n squared over 16. And we have 16 of these nodes for the next. So that layer's total amount of work is going to be 16 times n squared over 16, which results in a total amount of work of n squared for that layer. So here we can start seeing an obvious pattern. Because we are growing by 4 at each level, we are creating a multiple of 4 nodes per layer, but our amount of work done is also decreasing in kind of a very similar fashion. So because we have this n over 2, and then we'll square that work, they're canceling out. So by the more nodes that we create is being evenly distributed for the work between all of these nodes. So at each layer, we're going to be doing n squared work. And so what all that we need to do now is essentially find the number of layers and multiply that by n squared. So we said earlier that the number of layers we have is equal to log base 2 of n. And since each of these layers are going to be doing n squared work, we say that the total amount of work is going to be n squared log n. So if anyone has any questions, you can unmute right now. I think there's also a lot of great chat in the chat. But is anyone confused at any part of this?
How was the g of n factored into this?
Yeah, the g of n is going to be where the work is being done for every node. So each node has to call g of n. And this g of n is going to be doing theta of n squared work. So for any given function call, we take the input and we plug that into our g of n. So for the topmost layer, resulted in g of n of theta of n squared work. So the next layer, we have a size input of n over 2. So a single node plugged into this function would give us n squared over 4 work. And that these like boxes are representing the work done by that g of n call. So that's where most of the work is being done.
Okay, I didn't know the red meant the G of n, but that makes sense. Thank you.
Yeah, the red is just here to mark the work being done for like each of these nodes. Sorry if that was confusing.
Thank you.
Can you explain one more time why we're dividing by, or like why we could divide by the number of nodes on that layer?
Can you clarify that really quick?
Yeah, because like you said, it was like for example, for like the next layer, there's like 16, right? You said like it was like 16 n squared divided by 16, I think, which is
yeah. So I think I understand what you're talking about. So at any given point for the layer, our work is going to be kind of canceling out the work done by the number of nodes in that layer. So for our second layer here, we have 4 nodes, each one doing n squared over 4 work. Well, the next layer, we have 16 nodes, each doing n squared over 16 work. So there's a nice kind of cancellation here because we have some n squared over a constant, but that constant is going to be the number of nodes we have in that layer. So each layer is going to end up being n squared work. Does that make sense?
I have a question.
Yeah.
So for the final results, why is it n squared time log n? It seems like we're multiplying time per node by number of level, but I thought we have to also multiply the number of node in each level.
Yeah, I actually think this is a mistake right here. This should probably say levels. And the time per level is going to be equal to n squared, and we'll have number of levels be equal to log n, so we can multiply those. You're correct in saying that actually per node is going to be dependent on which layer we're on. So at any given layer, so like say this is layer 0, layer 1, layer 2, and so on, time per node is going to be given by n squared divided by 2 to the I, where I is given by the layer. So we can see the time per node at the 0th layer is n squared over 2 to the 0. It's probably multiplied by 2 actually, but n squared for the layer 1, we're going to have n over 2 to the 2nd power, so we have n squared over 4. So we're actually going to have n squared over 2 to the 2i time per node. Yeah, the total amount of time per level is actually n squared, which is why we multiply those two. Does that make sense?
Yeah, thank you.
Yeah.
And then I was just wondering, so are we squaring? So we're squaring every single number. So like with our example, if we do like 4, we'd square 4, 2, and 1.
Yes, you would
So
square every number. And that's
Okay.
because you are, every time you call F4, even when it's a subnode or whatever, you're always going to run G of n at the end, right? So whatever you pass in as n, you're going to have to square it for the runtime when that occurs. And that happens in every single node.
Okay, that makes sense. And then if there was no G of n, would the runtime just be log of n?
Not quite. So if the runtime, I can let Michael answer this, but if there was no G of n, then the work per node would be 1, right? It would be constant basically, because it's not dependent on n. And so because of that, instead, your total work would be the number of nodes in your entire tree, because every node does an equal amount of work. So that's like 1 plus 4 plus 8 plus, or 1 plus 4 plus 16, etc., which I can't do off the top of my head. I don't know if any of you guys can do it off the top of your heads, but yeah.
So what, it'd be n?
It would be the sum of whatever 1 plus 4 plus 16 plus 64 is. I don't necessarily know what that sum is off the top of my head. I think it's less than log of n, but it might be log of n, but it's definitely less than n, I think. I don't think you should have to know like what those sums are off the top of your head.
No, I'm not wondering what the sum is. I'm just wondering
Oh.
for the time complexity, if there was no g of n, would it
Yeah,
be?
if there was no g of n for any given node, it would just be constant time. So these red boxes would all be 1. So
Yeah,
all of the work would be just in like doing these like constant time operations.
Yeah, so would it be theta log n?
Yeah, like
I believe
like
it
I
would be
said,
log n. I think
yeah, I
that's the
think it
answer
is.
if you do
Okay.
the summation.
Oh, okay. All right. Thank you.
Okay, Tamer, do you have a question?
Yes, hello. I
Hello.
just had a small question about, so each node is giving 4 new nodes, right?
Yes.
Okay, so how isn't it n to the power 4?
So
Because,
yeah, we're not necessarily making 4. It's not like we're creating 4 new nodes. Well, we are, but the total amount of work being done is decreasing as we're creating these nodes. So we start with 1 node and we create 4, but the work done in this top node is evenly distributed between the work also done in these lower nodes. So for any given of these 4 nodes, we also do n squared work across them. On the next layer, we have 16 nodes, but we also do n squared work across all of them. So we'll go down until we hit the bottom, which is a log n height. And at that bottom, we'll have some, I think it is 4 to the log n number of nodes, but each of those nodes will be doing n squared work across all of them.
yeah.
So
So if,
go ahead.
so if
what were you
each
saying?
node is doing n squared,
If
and each node is giving
level,
4,
each level is doing n squared work.
each
So if you
level is
add
doing
up,
n squared,
each
even if
level
we
is
have,
doing n squared work. Yeah.
even if we're giving 4 new, like for example,
Yeah.
if it's 4, then it's,
So yeah, you see here at the topmost level, we had n squared. And when we halved the input size for each node, we resulted in a n squared over 4 work. So like for this node, I'll say right here, we do n squared over 4. And so each of these, that's a long 4. Each of these is also going to be doing n squared over 4 work. And if you multiply this by 4 for each of the nodes, then this will result in n squared work total for this layer.
oh,
This is actually going to be the case for
Okay,
every
okay.
layer.
okay. Thank you.
Yeah, no problem.
Thank you.
All right, so that is the end of the presentation, I believe. So if anyone has questions at this point, feel free to ask questions about anything.
Oh, could I ask a question about like the best case, worst case, and like using the big data versus
Yeah.
big N, big O, and big omega?
Yeah, definitely. So you had a question about a case where we had worst case, best case, and we didn't use theta, right?
Yeah, exactly. Like in the problem, if they didn't give like the data n squared data n to the 5th, like how would you
Yeah.
answer that in terms of the big O and big data? Sorry, big omega.
Yeah, I'm gonna just make like a small change to this to try to give an example of where we might have this. So give me a second. Okay, say we didn't have this function and instead we have some h function that takes in the array. Sorry, my handwriting is really bad on my trackpad. And say that this function is characterized by some big omega and big O. So this runs in, let's say, a big omega of n cubed, and say it runs in big O of n to the 4th. So now our worst case is still going to be the situation where our input n is odd and we go in this else case. but we can't use big theta to represent our worst case. So our n cubed and n to the fourth are still going to be greater than our n and n squared for the best case, but we can't use a theta because h isn't perfectly defined with theta. So in this case, the worst, oh God, I'm not going to spell that out. The worst case is just defined by having some lower bound on n cubed and some upper bound on n to the 4. And the reason why we don't use theta n to the 4 here is because our function h isn't dependent on the characteristics of n. So it's possible that h runs in our n cubed, but it's also possible that our function runs in the n to the 4. So here we can just, our best description of our function h is going to be these bounds on it. And so here we wouldn't be using big theta.
I see. Okay, so if it gives you explicit omega and O for their function, then you should use that for the worst or best case. So in the best case, in the if statement, if instead of saying theta of n, they gave like another big omega and big O, we would use that for the best case as well.
Yes.
Okay. Makes sense.
Yeah, this has a similar analog for best case. I think Anjali is about to say something.
Sorry, jump in real quick to correct some misinformation from earlier. If every node did constant work, the total runtime would be n. Yes, because for a tree with branching factor 4 with log n levels, you would get 4 to the log n as your total runtime, which obviously simplifies to just n because the 4 and the log cancel each other out. Sorry for any misinformation, folks. Even TAs have a hard time doing asymptotics in our head on the fly.
Thank you, Anjali. Yeah, I couldn't do that in my head either.
Just want to ask, what did you write in blue?
I wrote in blue just some function called h of array. Yeah, sorry, my handwriting's not the best, but this is just saying, like, say we have some function h and it takes in some input array, which we pass in, and say that this function h is described by these bounds. So it has a big omega of n cubed and a big O of n to the 4th.
Oh, okay. Yeah, get it. Thank
So
you.
in this case, the worst case would be described by big omega of n cubed and big O of n to the 4th.
Mm-hmm.
And then I was wondering, so sorry, when you said for the whole it's n rather than log n, when you said the whole thing you added up, is it that you're adding up all the, like you add up the bottom row, the next row, the next row, the next row, and you add all those up?
So in that case, we were adding up the total amount of nodes in the whole tree because each node was doing one work per node. And so the total amount of nodes came out to being 4 raised to the log n power, which results in, I think it's a log base 2. So that comes out to be 2n if you simplify that. And then just in terms of like big theta, 2n becomes n. So that's why it came to be n.
And wait, why are you raising it to the power versus multiplying it?
Yeah, we're raising it to the power because we have a branching factor of 4. And so the total amount of nodes is going to be increasing by a multiple of 4 at each level. So we have like 1 to 4 to 16 to 64. So that's why we have to use the log n as an exponent instead of a multiplication.
Okay, great, guys. So we have about 4 more minutes left. So if anyone has some last final questions, you can ask now. Otherwise, you can always ask for questions on Ed, and we will get to you pretty fast, hopefully around the midterm. And we will have office hours on tomorrow and the day after, where you can ask us questions directly.
For the recursion problems, when we have all the layers, could you repeat again, like when we only care about the last layer versus when all the layers matter?
Yeah, definitely. So let's see, which problem is that? So for this one, we were only caring about the last layer because the last layer was going to be dominating the total amount of work done. And I guess it's kind of something you have to analyze when doing this problem. And I think Schrains is probably more familiar with it if he wants to talk about it. But essentially, the total amount of work being done was increasing as we were going down the tree. So unlike the problem that I just walked through where the total amount of work was constant per layer, the total amount of work here is actually increasing by a factor of n. So at this layer, we had n work. At this layer, n squared work. As we keep going down, n cubed work. And when we reach the bottom, we have n to the m work, n raised to the nth power. And so because when we sum all of those layers up, we will see that n to the m is the dominating order of a growth term. That is why we didn't have to care about the rest of the layers.
In general, when you're looking at these tree problems, if you think about like writing out the summation of how much work is done on each layer, and you realize that either the top layer or the bottom layer has a term so large that if this wasn't a recursion problem, if you were just given this problem as an asymptotics is like n squared plus n or something like that, if you would get rid of those lower order terms, that still applies to this tree problem. So in this case, obviously, if you had n cubed plus n squared plus n to the first, right? You would get rid of n squared and n to the first. And that still applies here, even when that kind of coefficient, sorry, that exponent gets a little bit more abstract because it's larger. We're still going to get rid of those lower order terms that you would get rid of otherwise.
Thank you very much.
Yeah, no problem. Any last questions from anyone?
No, thank you so much. Have a good one.
Yep, thank you for coming.
Thank you all for coming. We'll have one more of these tomorrow that is covering all those data structures that we didn't cover yesterday. And so that's like disjoint sets and like hash tables and all that stuff. So I encourage you guys to come. All of these will also be posted on YouTube. So yeah, no need to stress if you can't make it. But yeah, good luck on the midterm, everybody. Bye.
Good luck, everyone.